So we've given a few examples of different types of sensors that are used in automotive applications. There are many more than the ones that we've discussed here. But one thing you've noticed is that many of them do similar things, measure position or speed, for example. And so we need to choose between all of these different possibilities. And the way that we do that is using a range of criteria. How much does the sensor cost? How reliable is the sensor? How accurate is the sensor? That is, how close is it to the actual true value? How precise is the instrument, is the sensor? Meaning, how repeatable is it? What's the resolution? What's the smallest amount of displacement that it can measure? What's the sensitivity? How much output is generated for a given change in the input? What's the range? What range of displacements can it measure? What range of speeds can it measure? And a final criteria, which may not be that intuitive, but which we'll talk about more in greater detail, is the speed of response of the sensor. So in general, it turns out that a change in speed or a change in displacement, it does not cause an instantaneous change in the output of the sensor. It takes time for the sensor to react. And so the speed of responses is an important quantity that needs to be considered. There are even instances where a quantity must be estimated without a sensor. And so the idea there is, instead of physically measuring some quantity, you instead have a mathematical model that you use to estimate the quantity or to sort of predict the quantity. One reason why a sensor might not be available is just because it's prohibitively expensive. Sometimes even a sensor might not even exist. For example, there isn't really a sensor for measuring the state of charge of a battery, and so a mathematical model in essence must be used to estimate that quantity. The use of an estimator can also improve reliability because in essence it can't break down. So far we've basically just talked about sensors, but sensors actually are part of a larger measurement system, and there are different elements to this system, the sensor itself, but also signal conditioning, and then a readout for the system or computation for the system. And each element of this measuring system may have dynamics, and it may introduce error. And so how these affect our larger control system needs to be understood. So the first stage of our measurement system is the sensor. It's dynamic. It may not react instantaneously. The output of the sensor may take time to react when the quantity being measured changes. And so we may need to model this sensor as a transfer function or a differential equation to understand how the dynamics affect the larger control system. We also may need to do some signal conditioning on the output of the sensor. For example, we may want to filter the output of the sensor to get rid of noise. We may want to amplify the signal to make it larger in order to drive an actuator or in order to improve the signal to noise ratio. We may also want to integrate or differentiate the signal. For example, maybe we're measuring velocity, but what we actually want is position. So we need to integrate the velocity signal to get an estimate of the position. Or maybe what we actually want is acceleration. So we need to differentiate the velocity signal to get an estimate of acceleration. And we may also need to do conversions between analog signals and digital signals. So a DAC is a digital to analog conversion, and an ADC is an analog to digital conversion. And each of these sort of operations may have dynamics to them, and they may introduce error that we need to understand. And then finally, this signal is then used to drive an output, a gauge or some sort of electronic display, or even to generate a sound from a speaker, or it's read into a computer where the computer then may do some calculation or computation based on it. So here's a specific example of a measuring system with the 3 different stages. The first stage is the sensor, where our sensor is an accelerometer. And so let's say that this sensor is attached to our vehicle, and as the acceleration of the vehicle changes, the sensor generates a voltage output. And if we look at this, it turns out that the signal is noisy. So this very high frequency jumping around doesn't actually reflect the acceleration of the vehicle. The vehicle itself is not having its acceleration jump so drastically. What this is noise on top of the actual acceleration of the vehicle, either due to electromagnetic interference or whatever. And so the first thing that we want to do with our signal conditioning is we want to filter out that noise. We want to send this signal through a low-pass filter to get rid of that noise. And that filtering can be done with a circuit, an RC circuit for example, an op-amp circuit, or it could be done in software. And let's say that this acceleration signal isn't actually what we're interested in. What we actually need is an estimate of the velocity of the vehicle. And so one way to arrive at that is to integrate the acceleration signal. And then let's say that the magnitude of the signal is too small. And so we amplify it to scale the signal up. And so now we have this voltage that's a reasonably large voltage, and it's proportional to the velocity of the vehicle. And then we want to read this in to our computer on board our vehicle in order to generate some control commands. And so in order to take this smooth analog continuous signal and read it into a digital computer, we need to do an analog to digital conversion. Specifically, we're just going to take this continuous signal and we're going to sample it at different periods of time. And then this stage 3, the computer can then use these inputs that it's reading in to calculate different things. Each stage of this measuring system, of this measurement process, can introduce error and can introduce dynamics. And so we need to, in essence, understand the effect of each stage.